Welcome back for Advent of Code Day 20. Looks like we got another grid with a start and an end. Picoseconds, the frequently held race condition festival. So we got S start, E end, walls, dots are the track. There's only one path here, which is really interesting. Programs are allowed to cheat. The rules for cheating are strict. Every once during a race, a program may disable collision for up to 2 picoseconds. So you can get rid of potentially 2 walls. This allows the program to pass through walls as if they were regular track. At the end of the cheat, the program must be back on normal track again, otherwise it will receive a seg fault and get disqualified. So a program could complete the course in 72 picoseconds by cheating for the moves marked 1 and 2. That seems like the non-optimal cheat. Wouldn't okay, or 64, this, which cuts out this whole area. Save 38 by doing this, and 64 by doing this. Every cheat has a distinct start position and end position. Cheats are uniquely identified by their start and end position. In an example, the total number of cheats grouped by the amount of time they save are as follows: 14 that save 2. Okay, so we need to do the full path once, then we need to do all of the cheat potentials, and then compare them to the original and see how many seconds they save, or picoseconds they save. Picoseconds are just turns in our case. You need a list of the best cheats. How many cheats would save you at least 100? So we have to calculate them all, as far as I'm aware. I wonder how much effort that's going to be in terms of computation cost. But if we have this, we already have a parser for this. So I'll drop in the input, and the answer here that we're looking for is, well, they don't give us the individual answer. How many? I don't know that this is even the answer to the test, because there could be more cheats than this. So 28, 34, 36, 39, 40, 44 if this is that. So if we get more than 44, there is potentially just more that can save at least 100. Or wait, no. Yeah, this doesn't even give us the list for the answer. Sick. So shrug. This just gives us like the list of picoseconds. So we don't even get the answer for the test today. So I don't think that cheats that are on the edges even work, right? Because if you go like here and then here, it doesn't work. Here and then here, it doesn't do anything, right? Like going out to the edge never matters. If there were 3 of them, you could potentially get around something. But I think also you could just go through this wall right here, right? There's a question around, yeah, so 1, 2 is here, where 1 is the start of the cheat and 2 can go into an empty space. So we don't actually need to take 2 walls out. Oh, actually, we can only cross 1 wall, thinking about this. We can disable collision for up to 2 picoseconds, but that means we have to be on a wall and then not on a wall. That makes it really significantly easier, honestly, because then we can just remove individual walls, right? So it's the opposite of what we did the other day where we placed a bunch of them. Now we're removing a bunch of them. It seems vaguely relevant that there's a start and an end position, but we don't actually need that for part 1. So I'm not even going to worry about it unless part 2 needs it. So then this is pathfinding, right? So the same thing we did the other day, exact same thing, except for anything that isn't on a wall can be potentially removed. And actually, we can reduce our search space even more. Anything that is next to at least 2 empty spaces is the only walls we need to remove, because like this removal wouldn't do anything for us. So if it's next to an empty space or the end, then it goes into the list of walls that we want to potentially try. Let's see, where else do we do capital E? I forget which day it is, so I'm kind of just using ripgrep to find the grid. I think it's day 16. So day 16, start, end, walls, hash set, etc. Here's our parser. Here's the map. We can grab the tokens. Probably grab this whole thing, honestly. We don't really have test cases today, which is kind of unfortunate. But basically, we're doing the exact same thing we did on day 16. So actually, I'm just going to dump all of that in here. And we want nom, glam, and pathfinding, or nom locate, glam, and pathfinding, in addition to the typical dependencies that I compile in. Not all of which are strictly required, but so we'll be working on day 20, part 1. This obviously does not do what we need it to do. These are rotations from day 16, but I think we actually want the like directional, which I think we actually did on 18. So this is actually the implementation that we want for our grid, more or less. So let me grab our directions here. I guess we could also have grid size, right? But we'll get that from our min max. And then this is directions.iter. So let's make our const up here. We're going to do directions, iter, maybe filter map or whatever. We end up with start, end, and walls for each map. Well, run first path find, right? So that we have the original. And then we will also run each path find with one missing wall if that wall has at least 2 empty sides. So that's what we need to do. This will be a filter map like this. We will start, which direction do we go? Do we have a direction? I guess we don't move just forward, right? We can move in any direction at all times. It's allowed to move up, down, left, or right. So we don't have this little starting thing that we used to have, which means that we can just get rid of that in all places. And we don't have the direction here. All we have is our 4 directions filter map. We don't, I guess we do need to check grid bounds. Well, we don't need to check grid bounds because we have the walls. So walls will keep us in line. And this will be what? We have a direction, position plus direction is the next position. And what are we, walls dot get next position is enough. I guess we need to do contains. Let's do contains. Let's do dot not, pull in the not trait, dot then sum next position. There's something wrong here. So let's get our compiler up and running. The cost is required. Cost is 1. Next position needs to be a reference. Direction probably needs to be dereferenced or not. Let's look at what the compiler says. We'll call this direction. That was a variable misname. So this then, this is our first run. Is that our first run? Yeah, I didn't do the second run yet. Let's debug first run dot one. And this is our, what is this? This is, I don't know. We'll just debug it. We can just access it. This, I'm going to lock into a to-do for later. So this will panic. And we get 84 for the length. Did we find out how long it actually is if we don't cheat? 84. So we're getting the right length here. We're getting the right positions. We need the list of all maps or the list of all walls that have at least 2 empty spots on their sides. So that will be walls.iter.filter wall, right? Directions.iter, same thing we do up here. Directions iter filter map, position plus direction. We don't need to do these interiors though, because we don't need to know the actual positions of the interior positions. So filter map walls contains next position. I guess we don't need to filter map here then. We can just do walls contains. And this isn't going to collect. This is going to count. It's going to be greater than 1 or greater than equal to, right? 2 empty positions. Well, no, we're counting the opposite. Wait, did I mess up earlier? Position, filter direction. That's direction. What position are we working with? We're working with wall. Cannot add double shared reference to double shared reference. Fine. We'll double dereference. So directions iter filter direction. If the wall position plus a direction is in, let's do not so that we get the count of walls that are empty. And that needs to be greater than or equal to 2. And this will be, I guess we don't really need to collect this because we can just keep iterating on it. Possible cheats, right? So then we end up with like a list of possible cheats and their positions. There's going to be a decent amount of them. So let's just check one of them. 8, 4, 0, 1, 2, 3, 4. So this one is a potential, or it's hard to select these. This one that I have my cursor over is a potential cheat, which is accurate. Technically, this is also a cheat. We should get all of those. So I'm not too worried about this at all. I assume part 2 is going to be something horrifically long running. So I guess we'll find out. Possible cheats. So for each of these possible cheats, we basically need to run this. And this isn't going to be an expect, right? So let's dot map this. And this is going to be wall. And this is going to be, I guess we filter map this, right? And this is not first run. This is the run. And we have additionally wall. So if walls contains next position, so I guess, what are we doing here? If next pos equals wall, or the walls doesn't contain the next position. So I think we just expand our truth statement here. And this turns into all of that. This gets its semicolon. Wall needs to be compared in a certain way. We have a reference. We need to dereference that. We aren't using this whole thing, so we're getting a little clippy warning on it. We've now done this for all of them, and this returns an option. So the ones that succeed will get passed through. The ones that don't will not. So here we will have, is it a tuple of path and cost? So then we do first run dot one minus cost. Then we filter for cost where cost is greater than or equal to 100 and then count. What's wrong with our, I'll add a reference there. So theoretically, this should give us our result. Again, because we don't really have a test case, I don't know the answer. It does have 0 on the test. So let's do no filter, and we have 90 total possible paths. Let's do an inspect here. I guess I kind of want this to include the wall so that we can check. That's really only a debugging thing though. So we can map over this, which is going to be like path cost. And we can turn this into like path cost wall. And then this is path cost wall. And I'm going to debug wall cost. And I guess I will also debug the diff. I forget what this diff needs to be. And this is path cost wall as well. Yada yada. This runs. We have first run 84 cost. First run cost 80, cost 76. These don't feel low enough to be any of the interesting cheats. Because for this test input, we could do 72 picoseconds by doing 8, 1. And we have a lot of, look for 72. Do we even have a 72 in here? We don't have a 72 in here. Maybe our list of walls is wrong, right? So directions, iter, filter, next position, like for this is next to each wall. So wall plus or minus like Y and X and whatnot. If walls does not contain next position, which would actually include some of the boundary walls I'm thinking about now. But if it doesn't contain and at least 2 of them filter through, then this should be a valid wall. I think we checked the walls earlier. So if we debug wall here, we're just going to get a giant list of walls. So wall 42, right? We print that out on 62. It goes through the filter map. We print that out on 85. Cost is 82. Which one is this one? This one is, we don't have a 64 or 38. I think okay, it saves 64. It saves 38. If it saves 64, it needs to be like 20, right? So we should be seeing lower numbers here. There's a 48 in there, right? Cost is 44 for 0, 14. 0, 14. 0. That's the bottom left corner. 0, 14? So the cost is 44 for 0, 14? Wait, no. That's for 7, 8. For 0, 14, the cost is 84. Okay, so we are including the outer walls, basically. So let's reduce our search space here by saying next pos dot x is greater than 0 and next pos dot y is greater than 0, and technically we should also be able to find the maxes here, but this should at least cut out the low end. And I'm going to change these to infos. I think infos will work better for us. Of course, things like wall need their debug representation. This is kind of a special tracing syntax, and this is diff. So now we don't see any output really. So if we go down to our test and we use test log test here, and I do rust log equals info, we should be able to see everything, and everything is a little bit easier to line up, right? So 12.6 costs 82. We can see the costs a little bit better because they're all in a line. Cost 20. Diff of 64 is 6.7. So we actually do have the 20 with the 64 diff. We have the 44. We have a 72. So I think we're generally okay with that. I would like to cull this down a little bit more. Let's do walls.iter.map. We're going to get the X max. So map, and this is going to get unwrapped because it has to be there. And this will be Y max, which has to be there. And where we do these zeros, we'll do range contains the next position, and same thing for Y's. If I can hit the Y on my keyboard without hitting other buttons. So this should keep us down even further. This should now only be interior nodes, and let's do cost less than or equal to what, like 75? I don't know. That gives us 49. We don't unfortunately know if these all count. So let's do what? This filter, this is not cost, this is diff. And let's get this wall out of here too. Just doing that in code because it's kind of straightforward. So we end up with a whole bunch of numbers here. Do we think this matches? Is basically the question. We will sort lines if we can sort. 5 that save 0, 210, 312, 312, 210, 14 that save 2, 20, 36, and 38, 20, 36, and 38, 40, and 64, then 2, 6, and 4, 8. So we got everything. This is everything for sure. The question is, what number are we supposed to have? Because this needs to run on 100. We don't have the test. We'll cargo run day 20, part 1, and see if we get an answer. Oh, that's the first run. Okay. I don't know if this is going to be like unmanageable amounts of stuff to track. I don't know how many we have. We panic, and because I am not returning our thing, so let's run it again. And this will log out the first run. The first run costs 9,352, which feels pretty big. Maybe we could have a better heuristic for calling that, but I don't know what part 2 is going to be. Let's submit this. It is correct. So what did we end up with? We ended up with a grid with a start and an end position, some empty spaces. We've done this parser already. I mentioned which day it was earlier. I think it was 18 and 16, maybe. Yeah, 16 is where we pulled this parser from. So if you want to see a deeper look into this parser, definitely go check that day out. We use nomlocate to get all the positions and everything, and we end up with the start position, the end position, and a hash set of the walls here. We get the X max and Y max of each of these vecs so that we can then do like bounds checking, because we don't want to replace any of the exterior walls for part 1. So we just want to skip them, not have to do the pathfind on them. We do our first pathfind to get the original cost. This gives us each 4 directions. This code we've basically already written in previous days. So we do the same thing for the next set for all of the walls that have at least 2 empty spaces on either side. This is going to have to change for part 2 for sure. Then we've got a bunch of like inspects and stuff here that we can actually take out at this point. A couple of unused variables. We only really need the diff, so these chains could also be like integrated in a better way, but I decided to keep them fairly separate because I feel like this is a chunk where we generate the new, like we filter out the potential walls, then we use those walls to pathfind on, and then we map that into the diff and filter out anything that's not the cost that we want, and then we count everything. So that feels pretty good in terms of program structure to me. This is going to be significantly different for part 2, it looks like. We can actually last 20 picoseconds. So on the 20th picosecond, or on the last picosecond, we have to be on an empty space, but otherwise fine. So now, in addition to all the cheats that were possible, many more are possible. This 6 picosecond cheat saves 76 picoseconds because it's basically, almost as direct as you can get. Because this cheat has the same start and end position. It's the same cheat. Oh, good. So we only have to like start somewhere and end somewhere, and kind of pathfind through the walls, if that makes sense. So I guess that's kind of like flood filly. Cheats don't usually need to use all 20. Cheats can last anything up to and including 20. You only get 1 cheat. If cheat mode is active and the end position is reached, cheat mode ends automatically. You need a list of the best cheats, but now there are more to choose between. Here are the qualities of cheats, or quantities of cheats, that save 50 picoseconds or more. Find the cheats using the updated cheating rules. Okay. This is what I thought the first part was, actually. When I started thinking about it, I thought this was going to be a multi-position kind of thing, but I didn't code it to do that originally. So we could do pathfinding on all of the positions. Do we need to find them all still? How many cheats would save you at least 100? Yeah, we need to find them all. So we need to calculate them all. So I feel like our solution for part 1 takes a little while. Let's run this. Yeah, our solution for part 1 takes like 8 seconds right now, maybe 7 without the compile. We are running in release mode, so we don't really have anything to gain. I guess we could do something simpler. If we do the cost at every node for the regular run, and then we do Manhattan distance is less than 20 for every position we could be at through walls, then I think that would be faster. So if we take our part 1 and we do pathfinding to find the first run, so this is the path for all of the initial positions, then we take that first run. We could do something from pathfinding that would find all of the paths. Our input is only 141 lines tall, So we've basically got two options. We can either like pathfind everything everywhere and then filter down, or we can manually do a cutoff at the kind of Manhattan distance. So if we look at our test input, we kind of have a 20? 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 20 kind of encompasses the entire test input. So if you use 20 picoseconds on this graph, then you can make it almost anywhere, which doesn't really help. So that's really only a limit that's going to apply to the actual input. But even the actual input is not saving all that much, because for a 100 picosecond or 100 turn like distance, then if our grid is 140 by 140, you can get most of the way across most of the grid most of the time. But what we can do is Manhattan distance, and we can do that on all of the empties. So we have the walls list, and we have the X max and Y max, which we don't necessarily need right now. Our first run will give us all of those positions, but what we really want to do is to be able to iterate over all of the pathfinding positions, right? All the positions that we could land on that are in the first run. We know there's only one path through this, so it's got to be in there. Once we have that, then we can kind of do Manhattan distance from where we are to any of those positions. And if they are, too far away or whatever, by like 20 or 100 or whatever we decide to do for test versus actual input, then that results in how far away they are. We add the place we started, the Manhattan distance, and basically the total minus the place we ended, and we end up with the cost. We do a subtraction of the total cost of the original path minus the cheat cost if it's lower, and then that's it. That should be everything. So I'll make this like original cost or original path and original cost. We never need to go backwards on the path. So I think we can do combinations. So if we do like our list combinations 2, we should get every starting position with every future position in order. And I think I'll do tuple combinations instead so that we can throw a tuple in here, get a little bit more type safety. And then we have start and end here. So let's work part 2. And if we look at what's going on here, we kind of have like start position 61. So cost 61 to get here to 710. And the end that we want to try to get to is 38, which is further along the chain, which is position 81. So if we do like start minus end dot absolute value dot element sum, that'll give us the total distance, like the number of squares that we would need to get there, which is the Manhattan distance. Of course, I will expand these variables a little bit for start cost and start, position, and end cost and end position. So we have the distance. The distance needs to be 20 or less. So this is going to have to be a filter map at best, maybe something else. So if distance is greater than 20, then return none so that it gets filtered out. And what do we actually need to do here? We need to do the distance for anything left, right? So start cost plus distance plus original cost minus end cost. And this is let cheat cost equals this. So really we need like original cost minus cheat cost for the savings. What are these value typed as? Distance is expected U size found I32. That's because start cost is a U size. So distance is always going to be a positive value because we did an absolute on it. So we can U size it up here. And then technically we have a U size here for cheat cost, and original cost is also a U size. It's possible that this could fail. The issue right now is just that we haven't wrapped it in sum, but this could panic. And then I think we've covered our bases on one position to another because we only move forward and we're only looking for empty spaces that exist on the path. So we're not really counting here. We're looking for a filter again. We're going to filter on the savings. If the savings is greater than or equal to 50, if I remember correctly. And that gives us 285, which, if I remember correctly, is all of these numbers added together. So theoretically, we have our answer here. And we didn't end up needing the Y max and X max. So this is going to have to jump up to 100. And this is day 20, part 2. And we get a answer. If we submit that, we get a gold star. Huzzah! Now, I can unveil that I basically went on a huge tangent today. I got the first one very quickly, as you saw in the video. And then for the second part, I actually made a huge mistake. And because the examples all show the cheats only going in wall directions, so like this cheat here stops when it hits the first open spot. Technically, like it keeps going. So cheat mode here is not actually over because it hasn't hit 20 and it hasn't hit the end. The only time cheat mode ends is if it's 20 picoseconds in, 20 turns in, or if you hit the end. So cheat mode is technically still on here. So I don't know why they're saying this is a cheat when cheat mode is still on, even though technically you're in the path here. So because of this phrasing, I thought that we had to only go through walls. So I started doing like pathfinding to make sure that we were only getting to like reachable nodes and stuff like that. But the answer was far simpler than that. It was legitimately just doing Manhattan distance. So another day in which I wish the explanation was a little bit clearer, that the test cases didn't overfit into a specific subcase. But overall, not too bad as a problem once you actually get what you're supposed to be doing. So the parsing from part 1 didn't change. Remove all of these unused. We don't need Xmax and Ymax here. So we do the pathfind for the first iteration. We get the original set of paths and the original cost by doing that. So we get all of the paths, all the positions on the path, and the cost that it takes to do that original path. We do that in basically the same way that we've done it every other day. We have a north, south, east, west directions array that we define as a const up here, iterate over them, filter map, collect them, yada yada. Here I'm debugging the original cost, which you can see here is 93.52 for my real input. We take that original path, we enumerate it, which gives us the cost of each position because they all cost 1. We use tuple combinations to get the combination of every position with every position after it. So that lets us take these two nodes and their costs, basically, do a distance for how to get there, Manhattan-wise, or taxicab distance, which is basically a 2D grid distance. If the distance is greater than 20, we return none here, which I just realized we left in for the actual answer. I think that's still correct. Yeah, it's 20 picoseconds. So if we take more than 20 turns to get to wherever we're going, then it doesn't work. We return none. Otherwise, we calculate the total cost of the cheat route, so the route that uses the cheat we just had, and returns the original cost of the original route minus whatever that cheat route costs. And we filter for only the answers that are greater than or equal to savings of 100. And that's it. We just count those and we're done. So I hope you had a great time today with Advent of Code, and I will see you tomorrow for the next one.